Thanks for having me here. So I realized as I was going through these slides that we actually omitted OmniExtend from the title, and we still got 200 people. So I guess Martin did a great job this morning popularizing our open protocol. Of course, this talk is about OmniExtend. And it was actually supposed to begin by Marjan Radi, who's the first of these listed authors. There are many more authors actually here. I apologize to those who I missed. And I'm the very last one, which means my contribution is infinitesimal. So I thought I could go through the same old 10 old tired slides and that nobody wants to look at, or I'll try something different. So I'll go through 5 old tired slides, and then I'll spend the second half showing the current state of GitHub, because things have changed and we've uploaded a bunch of stuff just yesterday. So if you still want to see Marjan speak, there's actually a good YouTube video that was prepared by our IV team at Western Digital. You can search for OmniExtend on YouTube, and you'll have Marjan explain for about 5 minutes how to hook up a 2-socket RISC-V system using off-the-shelf components. So you can buy a couple of FPGA boards, and in this video, she'll explain how to set them up, how to load the binaries, and run your own 8-core 2-socket system. This is my get out of jail slide where our lawyers thank you for listening to me, and as long as you understand it, we're not promising you anything. Okay, so what's OmniExtend? So you've heard this morning, and I guess most of you are aware of it from about a year ago. We announced it about a year ago. It is essentially transporting a coherence protocol that happens to be seeded from the RISC-V ecosystem, but it has nothing really to do with the RISC-V instruction set per se. And transporting these packets, PILink format packets, over Ethernet. Right? And the choice of Ethernet is probably controversial. You've heard the explanations a few times. I can explain it again. But I mean, the OmniExtend itself is really a document of 38 pages that explains how to pack headers with certain bits in certain places so you can transport PILink over Ethernet. But it's really more than that, right? The OmniExtend is really an idea. And the idea is that in this supposedly open RISC-V ecosystem, we ought to be able to connect any 2 of these components, CPUs, FPGAs, GPUs, what have you, to each other without having to ask permission. And this kind of sounds silly, right? But if you actually try to do this and implement it, you run into all sorts of problems. And so it's not that easy. So that was one of the main reasons for choosing Ethernet, because since 1983, this fabric has survived every recession, and it's still around, and it's still the most performant fabric you can get. Now, the idea behind Coherence Protocol, I'll try to spend about 4 minutes on kind of a crash course what Coherence Protocol means. But the idea is that you can do various things. And the reason this talk is titled Architecture is because this protocol is not about a specific point-to-point or a 4-socket system or whatever. The idea is that with this protocol, we want to free you to create different kinds of architectures that what you can buy today. And most importantly, right, we want to be able to connect these 2, like in the upper left diagram, 2 sockets, these noodles with a bunch of components represent the on-cores with a bunch of RISC-V cores. And so you can take 2 of these boards and hook them up to each other and have a 8-socket system or a 16-socket system, I guess, in this case. Sorry, 16-core system in this case. But our selfish reason as a storage maker was this lower left diagram in which we want to attach new kinds of storage to CPU caches directly. And for instance, if we have fancy magnetic RAM in the future that requires latencies that are much better than PCI Express and other peripheral interfaces, we can simply use the coherence port and have a very high-performant, low-latency interface. Now, make no mistake, right? OmniExtend is not about small embedded things and low-power things. It is all about scale-out and very high performance. And so what most of you, I imagine, want to do is something like on the right-hand side of this diagram where you'd have a switch. And in this case, you can use any off-the-shelf switch, Ethernet switch, right? And then you can connect any number of RISC-V SoCs or accelerators or storage/memory devices and scale it out as you wish. All right, so we've shown off this demo for the first time last year. It's a little bit over a year ago when OmniExtend was first announced, and it actually started working the day before that on December 7th last year. So on this diagram, you see 2 of these large FPGA boards with Xilinx FPGA parts, which are running Sci5 SoCs. And right now in the booth in the exposition center, you can see this demo system that has a barefoot switch. So 2 boards are talking to each other, and the other board is connected to a switch, and the switch is actually showing up as a coherence endpoint. So that we've, on this previous graph, we've actually demonstrated all these architectures in the lab, and we've tried a few others. So this all works, has been working for a year. And we've also published a paper at Hot Interconnects about 4 or 5 months ago. And you should be able to get it. If you can't get it, please send me an email, and we'll send you a PDF where we have the first performance measurements. Now, of course, keep in mind that this is all running at 50 megahertz in an FPGA, so these are very slow. So if you look at, for instance, the x-axis is the size of the memory test, the y-axis is latency. On the left side is the microseconds, and you see that fetching memory through a switch takes 4 microseconds. Now, of course, 2/3 of this latency is due to the fact that we're running on a very slow FPGA. So that's why we have a project in the works with Sci-5. So sometime next year, around October, I believe, if we're lucky, we should get this SoC taped out and available to most of you, I hope. So this is essentially the U74 SoC from the Sci-5 website with these red components added. And I don't have time to go into too much detail about what these do, but essentially these are PILink arbiters and serializers that package up PILink messages and send them across Ethernet so you can form multi-socket systems or scale them out through the switch or attach your custom devices. In addition to this, we've been developing a custom platform that we call Houdini. So this, Martin showed it this morning, right? So this is the bare board without the heatsink. The heatsink is actually bigger than what could be fit in this photo. And this is essentially just a barefoot Tofino switch, but instead of going to 3 meters of copper, we have these slots on the board, and we can plug in daughter boards and get much better signal integrity and slightly lower latency. By the way, if you're a member of Chips Alliance, you can download the Allegro files, I hope, now or in the next few days for this board and make your own. You probably don't want to because they're not that cheap, but if you want to do serious development on scale-out, this is available to you. Okay, so let me now spend about 4.5 minutes on a crash course into coherence protocols. And I'm not going to teach you coherence in 4 minutes, that's clear. I started doing this about 5 years ago, and I knew nothing until a person who's been working on this for about 30 years now explained it to me about a year ago. So now I feel that I have a pretty good understanding, but I still wouldn't trust myself to go and design a coherence protocol from scratch. So thank you, Sci-5, for doing this for us. Coherence protocols are very different. For those of you who've been working with the different network protocols, such as TCP/IP or generally IPv4, IPv6, this is nothing alike. Right? This is completely different. And I like to walk through these couple of slides and an animation that Paul Lomenstein and my group prepared for me to illustrate how different these behave than standard network protocols that you're familiar with. And the typical reaction of folks who come from the world of regular networking is to try to simplify these things. And I'm going to save you a lot of money and grief right now saying, no, don't do that. That's not the right direction. The only way they can go from here is to become much more complex. So if this seems complex to you, you haven't seen nothing yet. Because in serious CPUs, such as Power and Spark and so on, these protocols are far more complex than what I'm going to show you. So we're talking about PILink, in particular PILink 1.8. And PILink, with these protocols, we like to call them by this acronym like MOESI and MESIF and so on, or MSI, the simplest one. And these have to do with the names of the states of cache lines while they're sitting in the CPU cache. Right? So for instance, with the PILink, there's a bunch of these states, and if you look at the cache line while it's sitting in cache, you can describe its state by these acronyms MESI, which stands for these things that are listed. For instance, M state means that the cache line is dirty at this very moment, and it's also exclusively owned, which means that no other cache can own it at that one time. And that means that when eviction time comes, we also have to go and commit those changes back to the memory controller. Similarly, for instance, E state means that we're ready to write for it, so we have the exclusive copy of it. Nobody has the copy, but we haven't changed it yet. And S state means that we have a copy, but we have no idea how many other copies there are. Right? Now, to change between these states, we exchange coherence messages. And this is very vulgarized, by the way. This is very simplified, and it doesn't show the whole protocol. This is just an illustration how it works. So these messages have names like acquire, probe, release, and grant. And the short descriptions you can see on the screen, right, what they do. So for those of you who may have come from other coherence worlds, usually what used to be called invalidate in PILink is called probe. And so caches, when they want to emit these messages and change states of cache lines, not just caches, I keep saying caches, there are many players in the cache coherence protocol, right? There are all the caches, there are memory controllers, which we also call the lowest points of coherence. And then there are also DMA engines and accelerators, which may or may not have caching, but they will deal in chunks of data that are cache line sized. Right? So to exchange these messages, PILink uses 5 channels. And what I've noticed over the past year is that a lot of folks get stuck on this, and they absolutely, positively are sure that they can simplify this and use fewer channels. So I'm going to repeat again, please don't try to do that. We'll end up with even more channels and a whole lot more states as we get this protocol to be more serious and enterprise ready. So these channels, the reason there are 5 here is that you absolutely want to ensure forward progress in any kind of combination of messages coming in from any kind of parties. And if you have fewer channels, you can end up with a deadlock or a live lock and so on. And we've had long discussions for about a year now, privately between Western Digital and Sci5 on how this works, and we're convinced that this is pretty good. And it's going to only get more complex. All right, so this is a little animation that Paul Ovenstein prepared for us, showing a very contrived case, right? So this is an example of an architecture where you might have 3 levels of caching, L1, L2, L3. All these caches are inclusive, which means that if a cache line is in L1 cache, it's also in the L2 and L3 cache below it. And then at the bottom, you see this, I'm sorry, it's an empty rectangle. I should have added a label, which is basically the lowest point of coherence or the memory controller where the cache line is originally sitting. Now, if you imagine in the inclusive system with a messy protocol, you can actually end up in a state, it's a very simple experiment, you can do it on your laptop or on your phone, where all the caches have the exact same copy of the data, right? So any given cache line, if you write a piece of machine code that just reads one location, if you run this code on all the 8 hearts that are shown on that, each one has its own L1 cache, you pretty much will have a shared copy of the same cache line on all the caches. So in principle, in this diagram, you could have, I forget what it is, 8, 12, 13, 14, 15 copies of data. Right? Now, this is great as long as you don't try to write. The moment you try to write, what happens is, let's say that this third from the left heart issues a write command. Well, you can write, but you are not allowed to write before you have permissions on the cache line to change its state, right? So what you do is your cache actually sends out a command called acquire, or a message called acquire. And what's important to illustrate here is that with this whole protocol that I'll show you, there's actually no exchange of data. Right? There's no bits of data going across. The only thing you're doing is you're changing permissions throughout the system. Right? So this acquire command goes to L2. L2 says, OK, I don't have that permission, so I'm going to ask for the permission downstream. But at the same time, I have to make sure that this other L1 cache that's under my purview doesn't have a copy of it that's stale. So I'm going to send a probe, which is invalidate, right? And then the probe gets acknowledged, and that cache line is invalidated. And similarly, this L3 cache now asks for permission from the memory controller, but at the same time, it asks for a probe for the other branch of the L2, and so on. You keep going that way. You have to keep probing all the way out to all the caches in the system. And then the acknowledgements come back, and then once you've received all the acknowledgements, you can grant. So this is the first grant after 7 or 8 messages. And then you grant all the way back to the requester. Now, again, driving the point home, this was 13 message exchanges just to ensure that data you already had is available for you to write to change the state of it. Right? So coherence protocols are heavy. This is how the world works. Everything, including your cell phone, works this way. And they're only going to get more complicated. Now, of course, it's not that bleak. The situation is improved much by using something called a directory, where you keep track of who has what cache line, and then you can reduce the number of messages that you send and improve the scalability of the system dramatically. OK, so I have about 6 minutes remaining. So let me spend these 6 minutes walking you through the current state of GitHub. And I apologize. I hope you can actually read better than I can, because this screen is really tiny. But the first thing to notice is, for those of you, there's about 60 folks who are following the old GitHub directory. So the GitHub has moved. The reason being that we're not doing this in a Western Digital private GitHub repository anymore. We've moved everything to Chips Alliance. So if you go to the old page, you'll see this notice that the project is archived, and there's a link at the bottom. And if you click on that link, it'll take you to the new GitHub, which is the same GitHub, except that it's now Chips Alliance GitHub. And on there, there's a whole new directory structure. So I'll walk you through that quickly. So I believe the first thing to look at is the new directory called software. So the last year's release didn't really have any software support. Linux worked on one socket, and you could read the memory from the other socket, but you couldn't actually use the CPUs. So this has been fixed. There was a lot of work done both by Sci5 and by our guys at Western Digital. So now there's a directory software. If you click on that, you'll find both OpenSBI, and you'll see patches for the upstream kernel if you want to compile your own. And also, as before, we'll provide you with the binaries that you can put on an SD card and just boot without having to do this cross-compilation yourself. And this works fine, and I'm not sure. And that's interesting. This doesn't work. Oh, there we go. Here's, you can see this in the booth. There is a 2-socket system, and if you do cat CPU proc info, it'll show you that you have 8 hearts available, and you can run 8 threaded things. Okay, so the next thing, if you go back to the OmniExtend directory, so there's now 2 folders. There's OmniExtend 0.1, which was the protocol as defined last year. And we've abandoned that protocol because we've actually, after a lot of soul searching, decided to not bind ourselves to these programmable switches. So we've actually reverted back to L2 encapsulation. So now you can use any off-the-shelf Ethernet switch, including Broadcom, Cisco, whatever. So the old protocol is still available in OmniExtend 0.1 directory, and then this 1.0 directory has a couple of new things that I think you'll find very exciting. So the first thing you'll notice is there's a spec directory, right? So the new spec is uploaded now. And in there, you'll see 3 files. So there's a PILink 1.0, which is the exact same PILink protocol as on the Sci-Fi website. So that's the basis for OmniExtend 1. Then OmniExtend 1 document is the definition of how you package tiling packets. So there's goodies in it, like this is the header for the whole frame. Then this is how you pack the tiling messages into a frame. And then for each type of message, this is how you basically form the message inside the frame. This is great, right? This describes how the protocol works, but if you're actually sitting down and trying to implement it, it doesn't even get you halfway, right? It's very difficult to start from this point and to figure out how to write your RTL. So what we've actually provided there, this is also work of Paul Lowenstein. There's another file called state transition diagrams, and in that file, you'll see about 15 of these tables. So like I said, the 4 states of the MESI protocol, MESI states, these are kind of states that we refer to when the data is in a cache. But when you actually sit down and to write RTL, you actually have to implement closer to 150 states to have the whole machine, the state machines of caches work. So we've actually tabulated all these. There's actually a book on Coherent Protocols you can buy from Wisconsin and Duke. That shows how you construct these states, and so there's 15 of these tables. So in this document, you can basically sit down and start writing RTL with these tables in mind. All right, so the next thing I think is going to be exciting to all of you. You'll see there's a directory called EMU. That's not a bird, it stands for emulation. And the emulation, so we got a piece of feedback, right, we have academic collaborators, and this system where you plug in 2 boards, like the upper left one, you take 2 Sci-Fi boards, Xilinx boards, and run Sci-Fi cores on them. You still have to pay like 15 grand to buy the 2 boards. Right? The question was how to make this more available to more academic labs who are usually poor. And one idea was to try to use smaller boards, but then it's very difficult to port this to other kinds of FPGAs, and you have to spend a month that is better spent elsewhere. So we said, well, why don't we just try to emulate one of these so you can start development on a laptop and just buy 1 board. And that's basically what this EMU is. It's an emulator written in C by Tudang in my group that essentially emulates an entire PILink endpoint, right? Now, what you can do is you can run this on your laptop if you have the right cables, or you just buy a PC with a NIC. And you run DPDK, you run this simulator behind the NIC on the DPDK, and because we're now L2 compliant, you can plug in one of these SoCs into a PC, and you can start developing on the PC. Once you're happy, in principle, you could use some sort of a high-level synthesis tool and just take your code and compile it into a chip, and it will work exactly the same. So I think for education, this is a tremendous tool. All right, so finally, there's another directory that's new. It's called SIM for simulation. So the beauty of relying on an ecosystem, like a P4 ecosystem of these programmable switches, is there's hundreds and hundreds of people who are developing code. So there turns out to be an entire open source switch simulator that you can download and run. And we've basically repackaged that and added our own scripts. And there's actually a video that is linked from that directory that you can watch. So what this does is you can download this virtual machine, and you deploy this virtual switch that already has P code that translates, or transmits PILink messages. And there's a Python script that injects PILink traffic that's been pre-recorded. And then you can develop your endpoints in a completely virtual environment on your laptop without having to buy any hardware. All right, so I have 20 seconds left, and I'm going to stop right here, and I'm going to take a few questions, and I'm happy to talk to you at the booth. And tomorrow at 11:45, Paul Lowenstein is going to give a much longer tutorial on PILink in our booth in the hall. Thank you very much. Yes.
So with the new version of this protocol, L2 encapsulation, I can run this over a standard Ethernet 2 switch that knows nothing about this protocol, or is it an 802.3 switch, or what is it?
Yeah, it's correct. You can run any non-programmable switch, right? When the hardware comes, it'll support 100 gig switches. I'm not sure about 10 gig. Depends on what IP we end up with in the SoC. What's still missing is, so we're still doing point-to-point, right? We're doing two sockets. What we don't have developed yet, but it's coming very soon, is the discovery protocol. In principle, you should be able to describe a system of hundreds of these boards and assign each one an ID. Right now, we do that by dip switches, and there's only so many dip switches. So as soon as that's running, which is going to be months from now, you'll be able to hook up any number of these boards to any off-the-shelf switch. Now, there's some trickery about how you route through the switch. So we'll get to that when we get to that point. We're not quite there yet. But yeah, that's the goal. Go ahead.
Do you have any performance evaluation, or especially when the system scales up?
Yeah, so the question is, do we have any performance evaluation as the system scales up? The answer is no, we don't have any measurements yet except the two-socket system. It's a long answer, and I'm like a minute behind the time, so let's talk later. The answer is going to be, just in kind of a brief answer, is you're going to be slower than a custom switch and a custom protocol, but not by much, right? It's going to be small factors, and as you scale to very large sizes, these very large switches are really good at switching, so you're actually going to catch up pretty quickly as you scale to tens or hundreds of nodes. You're going to be almost as good as a custom-built protocol and switch. I think I see two hands. How much more time can we? Yeah, we have to cut it off. So yeah, catch me in the booth, and I'll answer all your questions. Thank you very much.